Hello everyone, I'm Zhen. It's my pleasure today to present a joint work with Yunpu Yuyi Wang, Stephan and Volker Tresp. In this work, we focus on learning from temporal notch graphs, where we use a graph Hawkes process to capture the underlying dynamics. Compared to semantic notch graphs, temporal notch graphs, or TKG for short, store time-dependent events instead of static facts. For example, the GDLT dataset extracts news from newsletters and uses the key information such as a quadruple of subject, predicate, object, and timestamp to represent an event. Here is a graph view of a temporal notch graph, where nodes correspond to entities and an edge corresponds to a predicate with a timestamp indicating when this event happened. Since each labeled edge represents an event, we can consider a temporal notch graph as a sequence of events, where edges with the same timestamp are considered as concurrent events. For example, there are 5 edges in the first graph slice. We have then 5 concurrent events at the timestamp t1, so on and so forth. Based on observed events, our task is to predict lengths in a future time instance. For example, t4 here. There are several tools for modeling event sequences, such as the Hawkes process, which is a self-exciting point process. Each event type K has a time-varying intensity that represents the expected number of occurrences of this event in a unit time interval. In the Hawkes process, past events conspire to temporarily raise the intensity of future events. When on Eisner generalized the Hawkes process by using a concurrent neural network to predict the intensity function called the neural Hawkes process. In the neural Hawkes process, an intensity function jumps discontinuously at each new event and then drifts toward a base intensity. And occurrent events can not only raise but also reduce the intensities. Therefore, the model can capture both the excitation and inhibition effects. Although the event time in existing temporal notch graphs, such as GDLT, is discretized, we use the Hawkes process to model discrete events in continuous time. The advantage is that we can predict continuous time when events happen. However, we can't directly apply the Hawkes process on temporal notch graph due to the scalability issue. More specifically, each possible link between 2 nodes represents an event type, namely a triple of subject, predicate, and object. The number of probable event types of notch graph is enormous. For example, there are 1.4 times 10 to the power of 10 probable event types in our dataset, while the training set only contains about 10 to the power of 6 existing event types. So the graph is very sparse. By addressing this issue, we developed a graph Hawkes neural network, or GHN for short, that can be applied to large-scale temporal notch graphs. In the following, I will take this object prediction query as an example to explain our model. Inspired by the score function of static notch graph embedding methods, we use entity and predicate representations to model intensity functions instead of using event-specific parameters. Besides, we focus on the influence of past events that include the query subject E1 and the query predicate P1. We call these events the historical event sequence of this query. By predicting the missing object, we feed this historical event sequence into an RNN and compute the intensity function. But the model can still capture information from other events because there are shared embeddings for entities and predicates. Modeling the intensity function using entity and predicate-specific parameters and narrowing the scope of past events enable our approach to deal with large-scale temporal notch graphs. Continuing with this query, the right figure shows that the subject entity E1 form 2 links with other object entities at the timestamp T1. To summarize these concurrent events, we introduce a neighborhood aggregation module that computes the mean of the object embeddings, where the big O represents the set of entity 3 and entity 4. Then we define an intensity function to characterize the graph-Hawkes process. First, we feed the historical event sequence into the neighborhood aggregation module, and then feed the results into a continuous time LSTM. After the CLSTM processes all events in the historical event sequence, we concatenate the hidden state vector with the subject embedding and the predicate embedding. And then we make an inner product between this output and embedding of an object candidate as a similarity measure. Especially for this object prediction query, we refer to this intensity function as the subject-centric intensity function for predicting the missing object. For an object prediction query, we choose the object candidate with the highest intensity at the prediction. We consider the link prediction task as a multi-class classification task where each class corresponds to an entity candidate. For the time prediction task, given an event type, we aim to predict its next occurrence time. We compute the probability density that a given triple occurs at time t according to the survival analysis theory. Then we calculate the expectation of the next event time based on the density function, where we use the trapezoidal rule to estimate the integral. We evaluate our model on two benchmark datasets, the GDLT and the SEWS14 datasets, where the first one contains about 2 million quadruples. Table 1 summarizes link prediction results on both datasets. We see that our approach outperforms all other baseline models, different from the baseline models with discrete state spaces. We model the probability of an event in continuous time. Therefore, our approach can compute the event probability at an arbitrary time sample, which enhances our model's expressiveness. For the time prediction task, we propose a plausible way to evaluate time prediction performance considering concurrent events. Otherwise, most ground truth value would be 0, as in a baseline model called no evolve. We compare our approach with LITSWE and no evolve since only these two models are capable of performing the time prediction task on temporal notch graphs. The figures demonstrate that our approach achieves competitive results on both datasets. There are several use cases of our approach. First, combining a data space of political events, we can develop a system to provide conflict early warnings. Besides, we can construct a temporal notch graph that stores healthy records of individual patients and apply our approach for risk assessment of patients. To summarize, we propose the graph-Hawkes neural network for forecasting on large-scale temporal notch graphs. We solved the challenge of massive event types, borrowing the ideas of the score function from static notch graphs. Also, we define a plausible way to evaluate the time prediction and the new metrics on temporal notch graph modeling. There are a few interesting future directions, such as enabling induction on new nodes and developing explainable approaches for the link prediction task. Thank you for your attention. If you are interested, please check our paper for more details.